Good morning, folks. I'm glad to be here again. This is my third time to attend this series of conference, and which is always a good one. This morning, we had some excellent presentations. From my point of view, I can conclude that the corner of the wheel is always a big concern to us, because we can see that the corrugation happens there, and the squeal noise happens there. Because squeal noise happens at the curve of the track, so it's also called curve squeal. Therefore, if we want to solve these problems, we have to know the contact mechanics at the curve of the track before we solve it. Up to now, we have conducted a lot of research. We have conducted the measurement, especially in the longitudinal direction. The reason why most research are focused on this kind of lateral direction because it's more easy to measure in this direction. However, on the lateral direction is not that convenient. But this lateral direction is what the core of the contact mechanics. So for my research, it's more about the measurement at the corner of the wheel. My presentation get these 5 parts. So for the measurement, we get a test rig developed in Australia, and for that we use it to measure the longitudinal the adhesion in the longitudinal direction and the lateral direction. Up to now, we found that the adhesion ratio increase. If we get the rolling speed increase, we will get the decreased adhesion ratio. If we get the increased rolling speed, and we will get decreased adhesion ratio. Of course, these 2 cases are all in dry conditions. But what about in wet condition? Because we get affected by the weather. Okay. And now we get some research conducted in the longitudinal direction. Under the y direction, we found that the adhesion ratio will get decreased. Then what about the lateral direction? For the lateral direction, we can adjust the rolling speed at a different rotation. And in my research, it is a concern, this part. At the end of this presentation, you will find the answer. Okay. So to get this question answered, we need to also need to set this kind of develop this kind of mathematical model. This model is based on Johnson and Coker, and the effect of rolling speed is also included in this model. So this is the friction coefficient. This is also investigated experimentally, and this is a test rig we developed. I developed a method to measure the angle tag between the 2 wheels, in which it is simulated the lateral creepage. The larger the angle tag, the larger the curvature would be. I also developed a method to measure the vertical force and the lateral force simultaneously, so we can determine the lateral adhesion ratio reliably. Okay. Okay, now we talk about the results. This result is simulated with current mathematical model. You can see that with the increase of rolling speed from 200 to 600 RPM, the adhesion ratio, the lateral adhesion ratio, will keep decreased. Here, we can see that the simulated friction coefficient decreases with the increased rolling speed, especially for the part of high creepage is here. And the simulated friction curves indicate an evident negative slope at a high creepage. So this is the negative slope at a high creepage from which, it can be the mechanism of co-skew can be illustrated, because that is kind of damping theory. And this result is the measurement under wet and dry condition at different rolling speeds, the 200, 400, and 600. We can notice that the adhesion ratio decreases when water is applied at the contacting phase at low speed. Is here. You can see that this is dry and this is wet condition. And for 400, it also decreases. But for 600, which is high speed, it's not that evident. So it's keep decreasing with the increase of rolling speed. The measured results correlate well with the predicted friction curve for the case of high speed at 600 RPM. So you can see that current mathematical model correlate well with the results at high speed, but for low speed, it's not that good. Okay. This figure illustrated the results on the dry and wet condition. And the presence of water at the wheel interface can change the effect of rolling speed on lateral ratio. First, we can see that the lateral adhesion ratio decreases with rolling speed on the dry condition. This is the dry condition. This is 200, 400, and 600 RPM. However, after the application of water, the trend just almost reversed. This is 600 RPM. This is 200 and 400. So we can see that after the application of water, the lateral adhesion ratio increases with rolling speed. Here we get some discussions. This figure is used to get the differences between measured lateral adhesion ratio under dry and wet condition. We can see that at high creepage, the differences between dry and wet condition is quite evident. It's at high creepage. For the small creepage, it's almost neglectable. And another is about the rolling speed. You can see that at low rolling speed, such as 200 RPM, this difference is very evident. But for high rolling speed, such as 600 RPM, the difference is almost neglectable. But there's still some difference. It means that the lateral adhesion ratio decreases a little bit, even at high speed. So the points are the measurements. This is 200, 400, and 600 RPM. And these lines are simulated curves using current mathematical model. We can notice that the correlation with the experimental measurement is quite good at high speed. For low speed, however, it's not that good. It means that the effect of rolling speed is not taken into account enough in this current mathematical model. Okay, so these points are listed here. To get this problem solved, we need to get this model developed further. So we introduce this expression into the new model as the expression for friction coefficient. And after simulation, we can see that the correlation with the experimental measurement is much improved, even for low speed, such as 200 RPM. Okay. Here are some conclusions. First, after the application of water, the lateral adhesion ratio decreases. So this is similar. This is similar to the in the longitudinal direction. This reduction is remarkable for low speed, up to 0.2. So this is very evident, because normally we see that the lateral adhesion ratio is about 0.4, 0.3, which means that 0.2 is a large value. In contrast, this reduction is almost negligible for high speed. The lateral adhesion ratio decreases with rolling speed under dry condition. This is also similar to the case in longitudinal direction. However, after the application of water, the main results show a trend that lateral adhesion ratio increases with rolling speed. Therefore, the presence of water at the wheel-rail interface can introduce positive friction characteristics. So this means this can, how to say, just reduce the negative damping effect. This is a unique discovery in comparison with that measurement in longitudinal direction. The model developed in the lateral direction can provide much better simulation results, and the correlation with experimental measurements are much better, and it shows that this can provide a better description on the real contact mechanics. So just like we are pushing this stator step by step, of course, the people before us had already done a good job, but we do a little bit further and make it uproot step by step. This is my research, and thanks for your attention. Your questions are highly welcomed. Okay, thank you.